Well, hey everyone, and welcome back. As promised, we are continuing our Layers of the Earth series, going from the crust inwards. So last time we covered the crust, which you'll recall is our cool, thin, solid, outermost layer. And then we take it one more step inwards, and we get to this big layer in here, which is what we call the mantle. Okay, so this is where our focus is going to be on this video. And very much contrasting many of the points we talked about with the crust. We said the crust is generally, at the thickest pieces of the continental crust, you'll see it extend to about 50 kilometers deep. So that's about the deepest point at which the mantle begins. That's the end of the crust. And that goes to almost 3,000 kilometers. That's how far the mantle extends, roughly 3,000 kilometers down below the Earth's surface. So before we were talking 0 through actually anywhere between 5 and 50 kilometers, depending on whether you're in oceanic or continental crust, to all of a sudden a depth of almost 3,000 kilometers with the mantle. So that just gives you a sense of scale. The mantle is infinitely larger than the crust. Naturally, also, since the mantle is closer to the core of the Earth, and as we talked about, the crust continues to get warmer as you get deeper into it, and as you get closer to the core, the mantle is significantly warmer than the crust. So recall that the crust is generally around 200 through 400 degrees Celsius at the mantle, at the contact between the two. Well, the mantle is on average between 500 degrees Celsius and roughly 1,000 degrees Celsius, on average. Obviously, at the boundary between the mantle and the crust, it's going to be cooler than that, and at the boundary between the mantle and the core, it's going to be a bit warmer than that. But that's generally the range you'll see it in. So yeah, the mantle, getting much hotter as we continue downwards towards the core. Now the other thing to talk about is the chemical composition of the mantle. Now I stressed in the last video that the crust is really the only solid layer. Well, the mantle technically is solid in that if we have to assign it a state of matter, it is solid. It's not a liquid. The outer core is more liquidy. The mantle technically is a solid, and similar to the crust, it is silicate. It is formed of silicate rocks. However, these are, due to the high temperatures and pressures, these are generally in a plastic state, or undergoing constant sort of plastic flow and deformation. So we get this sort of, like lava-y kind of slow, viscous solid. Because we can't really call it a liquid. But it is, there's that semi-solid sort of feel to it. That's what I like to call it. Which, yeah, the key word here is plastic, I guess. Basically meaning it'll just flow like if you've ever melted plastic. It flows in a similar fashion. And the flow is also important to another piece we'll cover later. And one final note, the top of the mantle, or where it touches roughly with the the crust, the boundary with the crust and a small distance downward, the very top sliver of the mantle is rigid. And that top piece, along with the crust, forms what's known as the lithosphere, which is a topic for another day, which lies directly on top of the asthenosphere. But yeah, just know that the mantle is technically solid, just in a constant state of flowing in a sort of semi-solid liquidy way. and the top of the mantle actually is rigid, and together with the crust they form the lithosphere. And those are most of the key points on the composition of the mantle. Now the mantle is also special in that it is responsible for tectonic plate movement. And this is one of the pieces where it's important to know that the mantle is in a constant state of flow, and that it is very a very sort of semi-solid state. Because you can imagine, sort of, if that's the Earth, here's the mantle down here, and then we'll just say we've got the crust. And maybe we have two different plates here. We'll put a small distance between them, even though any crack between two plates would be barely noticeable in real life. But just imagine you've got this sort of, this very warm, liquidy layer underlying this layer of cool, solid rock. Okay? Now the heat is generating outwards from the core, and this is where we get into the concept of convection currents that occur within the mantle. And a brief review, or if you don't know what convection is, that is simply the movement of heat through a medium. Usually air, but in this case, the mantle material. And the key concept with convection is that heat rises. So when you have convection, you generally have the warm air rising and the cool air sinking, right? Just think about your house. Usually on a hot summer day, you'll notice that the heat rises to the upstairs rooms, making, for example, if your bedroom's on the second floor, that room will be particularly hot, while the basement will remain much cooler than the rest of the house, because the cool air sinks downwards. And that's the way convection currents work, and we can think of them similarly occurring in the mantle. We have heat generated from the core that rises up here. It reaches the top, but then it can't pass through, or it doesn't pass through, only some of it is absorbed into the crust up here. So as this heat moves, the energy also causes the mantle to sort of be in this flowing state, so we've got this movement of the material. It goes upwards. And then, though some of the heat may be transferred through conduction, which is just the transfer of heat by direct contact, some of the heat will be transferred to the crust by conduction. The mantle itself, the material within it, obviously can't go any higher, so it just kind of pushes outwards. And a similar thing may be happening over here. You know, we've got a lot of these little cycles just occurring here. Maybe we've got some that comes up here and then pushes out this way. So you've just got all these little cycles going on here. And then the cool air falls and goes back until it gets close enough to the core that it's heated, and then begins to rise again. It's a cycle, see? Core heats the mantle, rises, hits the top, the boundary with the core, is pushed along the boundary, which causes tectonic plate motion, and then eventually it cools and sinks. And this just repeats itself constantly, which allows the tectonic plates to move for an infinite amount of time, as long as there's energy radiating from the Earth's core. So yeah, you can just imagine what would be going on here. In this case, we've got two that are pushing away from each other. So these two plates here would be pushing outwards. They are diverging away from each other. This would be a divergent plate boundary. these two are pushing together, so maybe we've got a small plate boundary right there. I'll just make that look like something. So we would see a convergent plate boundary right here. And then these two are actually moving in the same direction, so we would likely see nothing. Just this plate moving in the same direction. We'll call that our nothing plate. And that's all there really is to convection currents. The rising of the heat from the core pushes the mantle material up to the boundary with the core, which allows the hard, solid core, am I saying core? Excuse me, crust, the crust to be pushed very, very gradually, which results in our tectonic plate motion. So that was just a brief overview of some of the basic things about the mantle. Thickness, temperature, composition, and very important concept of geology, the convection currents that exist within it. Hopefully this was informative, otherwise good review. Hopefully you guys enjoyed, and I'll see you all in the next video.